Good day, stat students. So today we're going to go over Chapter 16, ANOVA. ANOVA stands for Analysis of Variance. So don't get confused about this. We are not doing an analysis of variance to analyze variances. We are using variances to actually compare three or more population means. All right. So please don't get confused about that. We are comparing three or more population means by using two different variances, and you'll see. All right. So if you had one single explanatory variable, and in ANOVA, we often refer to this as a factor with three or more levels, we're doing a one-way analysis of variance. One way meaning we just have a single explanatory variable. So maybe, for example, we have our response variables, the number of sick days over the course of a year, okay, that employees take. And then we have explanatory variable, that'll be our factor, different levels of vitamin C taken. So we have a placebo, 90 milligrams, 200, 500 per day, all right? So that would be a one-way ANOVA because we just had one explanatory variable. A two-way ANOVA would be if we had two explanatory variables plus two factors. So we have different levels of vitamin C and vitamin A maybe. And so there, notice we would have not just 4 different populations, we actually have 16 different populations because it's a combination of all these things, all right, of all the different combinations of vitamin C and vitamin A. And we had 4 from each, so that would make 16 different populations then, 16 different combinations, all right. Now we're not going to do a two-way ANOVA, we're just going to work with one-way ANOVA in this class. So the null hypothesis will be the following. Mu1 is equal to mu2 is equal to mu3 is equal to ... mu sub k, where k is the number of different populations. All right. So if you had 3 populations, you can stop at mu sub 3. If you had 6, you would say mu1 is equal to mu2 is equal to mu3 up through 6. Okay. H sub a, the population means are not all equal. Now students see that and they want to kind of get clever about it. Please don't try to get too clever with this. Some students will put mu1 is not equal to mu2, or comma mu1 is not equal to mu3, and comma mu2 is not equal to mu3. And so don't do that. Just put in the alternative that the population means are not all equal. Okay, it covers everything with that, just with that one sentence. Now, this is not exactly how the tests are run. However, it is a very good way of thinking about it. Let's say that you had a confidence interval for mu1 that you made by its, you just went ahead and took the data from the first sample and made a confidence interval based upon x bar 1. And then you made a confidence interval for mu2 based upon x bar 2. And then you made a separate one for mu sub 3 based upon x bar 3. Okay. So let's look at, say, mu1 versus mu2. Notice that here, once I threw in the numbers, all right, and you can see that what? They overlap. So the confidence intervals for mu1 and mu2 overlap with one another. In other words, there's a reasonable possibility that mu1 is equal to mu2, all right? Well, let's take a look at the confidence intervals for mu2 and mu3. Notice the confidence intervals are still overlapping, right? So there's some numbers, all right? And so there's a reasonable possibility that mu2 is equal to mu3. Well, take a look at the confidence intervals for mu1 and mu3. So notice they are not overlapping anymore, are they? All right, so I throw in some numbers. Here we're relatively sure that mu1 is not equal to mu3, and the confidence intervals don't cross one another. And the ANOVA table that would be constructed would probably have a p-value less than 0.05. We usually run these ANOVAs just like regression at 0.05, and we would reject the null. And because that's what the test is picking up on, is that there seems to be a difference between mu1 and mu3. So it's kind of strange. mu1 could be equal to mu2, mu2 could be equal to mu3, but mu1 and mu3 are far enough away from each other that we can say that there's probably a difference there. Okay, so if that was the case, that would tell us that that the population means are not all equal. All right. So let's say that we had this example, all right, where you had the confidence intervals and the X bars pretty far spread out from one another. And if you were, now again, this is not exactly how this is conducted, all right? But again, it's a reasonable way of thinking about it, that if the confidence intervals are not crossing one another, that the p-value would be extremely small in this situation. It's not going to be, you know, 0.03. It's going to be 0.00000000001. Okay, because it's so overwhelming that these things are so far apart from one another. Okay, and that how the numbers are suggesting that there is a huge difference between all of them. All right. Let's say that we ran into this situation. So notice here that that it is certainly a possibility that mu1 could be equal to mu2, right? Mu2 could be equal to mu3, and mu1 could be equal to mu3. All right, all the confidence intervals cross one another, and so the p-value in this situation would be greater than 0.05, and we would fail to reject the null. If you had this situation where you got a ton of overlapping between mu1 and mu2 and mu3, all right, the p-value would be extremely large. It would get very close to 1 in this situation, okay? And we would definitely fail to reject the null in this, okay? So we would definitely have a do not reject the null hypothesis. All right, let's head over to the table. Now, with regards to the ANOVA table, this is easier to construct than it was for the regression. Okay, with regression, there's a lot of calculations that go on here. Here, with the ANOVA, it's not so bad. So let's go through the calculations, all right? So first of all, this book uses groups for the first source of variation. Other books will call it treatments, whatever, okay? But I guarantee you that the first line is always meaning the same thing, okay? They're not going to get mixed up in computer programs. The second one is always going to be error, and then the total. All right, so you have degrees of freedom for the groups, you have SS for the groups, and you have MS for the groups. And same thing for error. You can add those up to get a total for the degrees of freedom and total for the sum of squares. For the mean square, doesn't make any sense to add those guys up. All right, so we don't. All right, so just like before, as you move down the table, things add. Now, as you move across, though, notice what's going on here. Things are dividing. So if you took, just like before, to get MS groups here, you would take SS groups and divide it by its degrees of freedom. MS error would be equal to the sum of squares for error divided by the degrees of freedom for error. Okay, and then to get the F stat, it would be this guy right here, MS groups, all right, divided by MSE. And it gets your, and this guy right here would be the test statistic. And it's in terms of the F. All right. So the degrees of freedom for the groups, let's start with that. Oh, by the way, you only need 4 numbers to complete this table. You need this number right here, you need this number right here, you need this guy right here, and you need this one right here. If you have those 4 numbers, you can complete the table, all right? Because then it's just a bunch of either adding or dividing, all right? So the degrees of freedom for groups, that's k minus 1, where k is the number of populations, all right? The degrees of freedom for error. Notice, please note, it's a big N here. It's a capital N minus K, where capital N is the total sample size of all the samples put together. So it's the summation of all the individual sample sizes from each of the groups. All right. So you'll see, I'm going to go through an example here, and you'll see capital N later on. All right. please note, is the summation of all the sample sizes from all the different groups. All right, what about SS groups? Let's figure out what that is about. So the first thing that I want to point out to you guys, and pay attention to this one because this is why we call it an analysis of variance. So notice the variance formula. If we go back to the variance formula back in, I don't know, chapter 2 or something like that. Remember what the variance formula was? It was the summation of x minus x bar, and then we got a square divided by n minus 1. And really, I didn't tell you this back then, but really what the variance is, it's the total variation in x divided by its degrees of freedom. That's what a variance is. It's the total variation, all right? So what would be the total variation? Total variation in the numbers would be taking each one of the observations, subtracting off its mean, seeing how far apart they are. We've got to square them first, get rid of the corresponding compensating positives and negatives, and then you sum it. That would be actually the total variation, and then we divide by a degrees of freedom to get the variance. So that's what a variance is. SS groups is the total variation, okay? So it's this number right here between the different groups. That's what it is. It's the numerator in some way, shape, or form, all right? So here's the formula, okay? And I'll get to n sub I here in a second. So x bar sub I, okay? What is that? That is the individual sample mean from, say, the first group, from the first sample, all right? And then x bar 2 would be the sample mean from the second group, okay? And then x bar is the overall sample mean. It's the overall sample mean. So that means if you put all the data together from all the different groups and averaged it, that would be x bar in this calculation. So notice x bar. So notice here we have individual observations, the different x bars, okay? Then you have an overall sample mean, this x bar. Notice that it's pretty much that. It's just that we're weighting it based upon some sample sizes here, okay? So let me give you an example. Let's say x bar 1 is equal to 3, x bar 2 is equal to 7, and x bar 3 is equal to 8. Assuming the sample sizes are equal, do you see how x bar, the overall mean, would be equal to 6 then? So let's see, 3 plus 7 is 10, plus 8 is 18, divide by 3, you got 6. So as long as the sample size are equal to one another in the three different groups, x bar, the overall mean, would be equal to 6. So the n sub I part of the formula suggests that we are weighting the differences based upon the sample size. All right. So SS groups, okay, is saying, all right, if here's x bar 1 at 3, all right, so this was at 3, another one was at 7, another one was at 8, so this is x bar 2, x bar 3, all right. All we're doing is saying, okay, well, here's the overall x bar of 6. We're seeing how far away 3 is from there, how far 7 is away from there, how far 8 is away from there. And what is that? That's just the numerator of the variance, okay? It's the total variation. So MS groups, notice that what are we doing? We're taking SS groups, which was a total variation, and dividing through by its degrees of freedom. Okay, so MS groups is basically a variance now. Okay, it's a variance. And it's the variances between the groups. How much variances are there between group 1, group 2, and group 3? And so we look at the different X bars and see basically how far apart are they. All right, so that's what the numerator part of the FSTAT is. Okay, now more insight into SS groups. And this you really should pay attention to. You know, people hear, oh, more insight, great. This really explains it, okay? So bear with me, all right? Kind of pay attention here really close, all right? So let's say that we had our 3 different samples, okay? And so we got 3 populations. We took a sample from each one, and here are the numbers, all right? And X bar 1 turned out to be 5, X bar 2 turned out to be 8, X bar 3 turned out to be 11, and there's the different box plots for them. The overall mean turned out to be 8. So 5 plus 8 plus 11, all right, that's 24, divided by 3, that you get yourself 8. Since they all have the same sample size, you can do that. And notice that the sample standard deviations are roughly the same and very small. Okay. All right. Now, here's a second example. All right. Keep that in mind, what I just told you. All right. But here's a second example. We're going to compare example 1 versus example 2. Notice X bar 1 is still 5, X bar 2 is still 8, X bar 3 is still 11. So we do have different numbers up here. If you compared it back to, notice how the numbers are changing up at the top here. So the numbers are changing, all right? So the overall mean is still 8, but what happened to the standard deviations? The standard deviations are definitely increasing, aren't they? Okay, they're getting larger versus example 1. Okay, so instead of having 1, 1, and 1.25, we have 5.66, 4.69, and 4.30. So the standard deviations are definitely getting larger, but the sample means did not change. They're still sitting at 5, 8, 11, and the overall mean is still at 8. All right, so here's the ANOVA for the first example. And here's the ANOVA for the second example. And definitely what we need to pay attention to is that SS groups are exactly the same between the two. Why? Because the sample means and the overall mean were exactly the same for both. So you're going to get exactly the same number for SS groups. Okay, so this is measuring how far away the X bars are from one another. All right, so notice what was different about them. What was different about those two groups was the standard deviation between, the standard deviations were getting larger, okay? So, so what would make SS groups larger for either example? If the mean started to separate further, all right? So for example, if you had 5, 8, and 11 and the overall mean was 8, SS groups would be 90. But notice if I made them further apart, okay? So instead of being 5, 8, and 11, now it's 0, 8, and 16. The overall mean is 8. What's going to happen to SS groups? It's going to go up. Why? Because they're getting further apart. So the further apart they are, SS groups goes up. That means what could happen, okay, is that this increase in SS groups would lead to a much larger F-stat, okay, because the X bars are further apart, which would lead to smaller p-values, which would mean to reject the null hypothesis, saying, hey, we got a difference between at least one of these population means from the other ones. All right. Well, let's go in the opposite direction with the means, meaning they get closer. So in this silly situation, we would have X bar 1 is equal to 8, X bar 2 is equal to 8, X bar 3 is equal to 8, the overall mean is equal to 8, and that means SS groups is 0. Okay, so notice that what would happen there, the F stat would turn into 0, okay, and there you go. And we definitely can't tell a difference here based upon our random samples. All right, how about some insight into SS error? Okay, the sum of squares for error. All right, so SS error is this formula. It is the variances of the individual groups weighted by their sample sizes, okay? And then we go ahead and sum them, all right? And so if you kind of think about it then, what's going on here is that, remember, this guy right here is just this formula right here. And so since we are multiplying by the individual n minus 1s, notice what would happen here. The n minus 1s would cancel out, and all you're left with then is this, all right, for the different groups, okay? And it's the summation of that. So kind of think about it, all right? But it's the summation of the sample variations. That's all it would turn into. And so MS error is also a variation and is a different variation than MS groups. This is actually measuring the different variation uh, within the different groups, okay? And we're kind of bringing them together, we're kind of pulling them together. That's what's happening here. We're pulling them together, right? So notice the ANOVA here that for our first example, the error was very, very small because the standard deviations in the groups were pretty small, all right? And then what happened down here, the variations, SS error got a lot larger because the variations, okay, the variances in the groups were getting larger. We saw that, right? And so SS error would get larger. So you can read those three sentences there, but no, I just explained that. Okay. So notice what happened up here is that the f-stat is pretty large here, okay, for the first example, and the p-value is extremely small. And then what happened to the f-stat here? It got pretty small because of the pretty large standard deviations there, okay, and eventually they would get squared for the variances, and then the p-value turned out to be fairly high, right? And basically this is saying we can't tell a difference. We definitely have some differences here, okay? All right, so here's an example. We give math problems to 3 first graders, 2 second graders, and 4 third graders. We test if there exists a difference in the mean times in minutes to complete the problems for all students in these grades. Now, I can't give you a bunch of data, okay? We can't make an ANOVA table with a bunch of data, okay? I can give you a small data set, okay, and work with it. So we have our first graders, 3 of them, second graders, we've got 2, third graders, we've got 4, okay? So notice N1 would be 3 in this situation, right? Got 1, 2, 3. And 2 would be 2, 1, 2, and then 4. And 3 would be 4. That means the overall N is the summation of these guys here. So 3 plus 2 plus 4, okay, that's 9, capital N. K is equal to 3 because we have 3 populations that we're taking a look at. First graders, the second graders, and the third graders. So X bar 1 is equal to 14. So if you average these numbers right here, that would turn out to be 14. If you average these guys here, oh my goodness, they'd turn out to be 9. And then if you average these numbers right here, you get 3. Okay. Now you got to be careful here. Notice I made the sample sizes different. I made the sample sizes 3, 2, and 4. So you cannot mathematically simply then take these 3 numbers and divide by 3. It won't work mathematically. You need the sample sizes to be exactly the same. And they certainly are not here. So what you would have to do is you would have to take each one of these numbers, the 10, the 14, 18, 7, 11, 1, 2, 3, 1, 2, 3, and 6, and divide by the total that we had there was 9. Okay, and that's how I got 8 for overall X bar. S1 turned out to be 4, S2 turned out to be 2.83, S3 turned out to be 2.16. So I just threw that in the computer to get those. All right. Probably I wouldn't make you figure out the standard deviation between the, for all those groups. I'll probably just give them to you if I wanted to actually work with the ANOVA. Okay. So that means the degrees of freedom for the groups, that's k minus 1, that would be 2. The degrees of freedom for error, that's n minus k, big N, right, capital N. So we have 6. SS groups, all right, so let's be careful here. So we have N1, which is 3, okay, got that. And then we have our first X bar 1, which is 14, minus X bar, the overall X bar of 8, and then we square it, all right. Then we have 2, all right. Then we have 2 for N2, and then we got X bar 2 of 9 minus 8. Let's square that. Then we have a sample size of 4, all right. X bar of 3. X bar 3 is 3 minus 8 X bar, All right, and when you do the math, I came up with 210. How about SS error? All right, so we got to go ahead and take the standard deviations. We had 4, 2.83, and 2.16, right? And so we go ahead and square each one of those. So we square the 4 and multiply by n minus 1, and then keep on doing that, right? And if you probably did this in your calculator, you're probably not going to get exactly 32, 8, and 14. However, I left all the, I for these numbers right here, I broke it down to just 2 decimal places. But if you took it to all the decimal places, all the significant decimal places, that's what would turn out here, 32, 8, and 14. So SS error turned out to be 54. Don't expect these numbers to come out to a nice whole number every time, right? All right, so I got our 4 numbers, right? So for SS groups, we got 2 degrees of freedom for groups is 2, degrees of freedom for error is 6, sum of squares for groups, 210, sum of squares for error, 54. And notice we can start adding things, right, to get the total. We can start dividing stuff. All right, so MS groups turn out to be 105. MS error turned out to be 9, 54 divided by 6. And then our F stat turned out to be 11.67. Okay. Now, at this point, we would have to go to the StatCrunch to go figure out the p-value. So I got smart here. I made some pictures and just kind of pasted them into my presentation already. So if you went into StatCrunch and went to stat calculators and then the F distribution, okay, the F distribution, and then you got to be careful here. So the numerator, degrees of freedom, I put as 2. Now, why did I put that as 2? Because that's the numerator here for the F-stat. So that's the group's degrees of freedom. That was 2 and 6. 2 and 6, right? So I put in 2 and 6, and I put, this is a right tail test, all right? And so I put a greater than sign, and here is the test stat. And here's the p-value. Turned out to be 0.0086, it looks like, rounded to 4 decimal places. So we would have rejected the null hypothesis here, and we would have said, oh, we got a difference. Okay, we definitely have a difference within these means. All right. The assumptions for ANOVA are the following. So the samples are independent random samples. We need independent, right? Random samples. 2, the distribution of the response variable is normal, or the CLT applies. So you can't have these extreme outliers in the data. And so we should check for that. We should check this with some plots. And so if you do an ANOVA for your project, okay, in order to check this, you should go ahead and take a look at some plots, at least one plot. Look at maybe a couple of histograms, 3 histograms, look at box plots, something, dot plots, all right? And at least tell me if you think it's normal or not. Now, in your project, if the conditions don't apply, I would just keep going, okay? But tell me in the explanation in your write-up that, hey, I think the assumption for normality was broken here, or, you know, because we didn't have a large enough sample size, okay? So now, when I say the CLT applies, what I'm saying here is that not the overall n. Basically, you would need n1 to be greater than or equal to 30, right? You need n2 to be greater than or equal to 30. You need n3 to be greater than or equal to 30, since we had 3 different groups, okay? So that's what I mean about the central limit theorem applying. 3, all populations have the same standard deviation. If they all have the same standard deviation, we can call that overall standard deviation then sigma, okay? Because that means they all came from a one overall population, okay, that had sigma for it. And then when you broke it down into different groups, the standard deviation was pretty much the same for each one of those groups, okay? So you can kind of call the standard deviation for all the different populations then sigma. So The samples are independent random samples. All right, so probably that's going to be stated in the problem somehow. When you do your project, tell me if you thought that you did things independent and randomly. 2, the distribution of the response variable is normal or the CLT applies. So small deviations from normality is okay, especially if the sample sizes are large enough, right? And what did I say was large enough? Greater than or equal to 30. So like I said, we should look at some sort of plot for each sample. All right, how about the third one? All right, let's slow down with the third one. So there is a test to compare population standard deviations. However, it is not very reliable. It's very dependent on sample size and if the populations are pretty close to normality already. So we're not going to do that. Okay, what we're going to do, we're going to use a rule of thumb. All right, so here's the rule. As long as the largest sample standard deviation, all right, largest sample standard deviation is not more than twice the smallest, we can say that the population standard deviations are close enough to being equal at that point. All right, so we don't want large deviations within the sample standard deviations. So here's our problem again, all right, and what we're going to do is that we're going to actually run through the 5 steps. Since we have everything, we have the ANOVA and so on and so forth. All right, so there's the null, there's the alternative. I stopped at mu sub 3 because we only had 3 populations. Verify the conditions/assumptions. All right, with the sample size so small, really we can't verify the normality assumption. However, in a real study, we certainly can't skip the step. So hopefully we did take our random samples, and hopefully that we can go ahead and either say that stuff is normal or we took large enough sample size. Here, we're going to have to assume that the populations are normal with such small sample sizes. Okay. What about the population standard deviations are equal? Well, let's verify that. So S1 was equal to 4, S2 was equal to 2.83, S3 was equal to 2.16. Since the largest sample standard deviation, which is this guy right here, which is equal to 4, is not more than twice the smallest. So what's twice the smallest? 4.32. So this, okay, is definitely less than the 4.32. Population standard deviations are equal is verified. So a rule of thumb there. We calculated the test statistic based upon the ANOVA and our p-value. So since the p-value is less than alpha, we're going to reject the null, like I said before. And we have statistically significant evidence at the 5% significance level that the population means are what? Not equal to one another. All right, they're not equal. So since we rejected the null, we need to figure out which population means the test picked up that are different. All right. So we aren't going to make a 95% confidence interval for each possible difference. Okay, remember I told you that at the beginning that looking at individual confidence intervals based upon just all that sample information, we were not going to do. Okay, and so we don't do that. Okay, it was a good way of thinking about the differences between maybe mu1, mu2, and mu3. Okay, but we're not going to make a 95% confidence interval for each possible difference. Here's why. Let's say that you create a 95, let's say you create a confidence interval at 95% confidence for each possible difference in population means. All right. That suggests there's a 5% chance of a type 1 error for each confidence interval. Would you agree? All right, 95% confidence. So there's a 5% chance of a type 1 error for each confidence interval. Therefore, if you have 3 populations, that means you would have to make 3 separate confidence intervals. And so if you do the math and you take 1 minus 0.95 to the third power, you get 0.143. And what that means is that there's a 14.3% probability of making at least one type 1 error. And that's not what we want. We want the probability of making at least one type 1 error actually just 5%. We don't want it to be 14.3%. And notice how it exponentially goes up. And if you had 4 populations, you do the math, you actually would make 6 different confidence intervals. And that turns out to be 0.65. That means there's a 26.5% chance of making at least one type 1 error. Definitely don't want that. We got a one out of better, just slightly better 1 out of 4 chance of making at least one type 1 error. That's not what we want. We want that number to be 5%. Okay, this is what we call the family error rate. Okay, so the 26.5% is what is called the family error rate, but we want the family error rate to be 5%, not 26.5%. So there's a solution that a very famous statistician came up with, okay, and that is to create Tukey's. It's not turkey, all right, Tukey's confidence intervals that will make the family error rate 5% then. Now, this is a very complicated method with a very complicated probability distribution. Okay, so we're not going to go through the calculations. All right, we'll allow the computer to do that for us. All right. Now, when you are ready to do this in the ANOVA, okay, for either homework and do it on the computer, or you're going to do this for your project, when you do the ANOVA, at the bottom and there's a checkbox for, hey, do you want Tukey's confidence intervals to be created? And you just check that, and there you go. Okay. All right. So this is what came about with the different confidence intervals. Okay. And so again, this would make the overall error rate 5%, these confidence intervals. Okay. All right. Now you got to be careful here. You got to be careful. And this is not exclusive to StatCrunch. Every computer program does this. This way John set it up. Okay. And so notice what this says. The first is subtracted from the second. The first is subtracted from the third. All right. And then you come down here. The second is subtracted from the third. All right. Subtracted from. All right. So that means that first line right there, okay, that first line means mu2 minus mu1. That's mu2 minus mu1. The next line is actually saying mu3 minus mu1. First subtracted from. All right. And then the last one is mu3 minus mu2. All right. So you have to pay attention to that. Okay. And then here, now you can look at the confidence intervals and go ahead and use that logic where if the entire confidence interval is positive, the first value is greater than the second. If it's entirely negative, the first value is less than the second. And when you have a negative positive, you don't know. It's inconclusive. So I think you would notice here, negative, positive, oh, but this one right here, two negatives, okay? So that's telling us something. So notice the p-value there is what? Less than 0.05. And for the other two, it's greater than 0.05. So since this one's less than 0.05, what that's suggesting is that the confidence interval is going to be either entirely negative or entirely positive. Here, it's entirely negative. So since Tukey's confidence intervals for mu3 minus mu1 is entirely negative, the ANOVA picked up on what? That what? Mu3 is less than mu1. Mu3 is less than mu1. That's what it's telling us. All right, or if you will, mu1 is greater than mu3. Okay, however you want to think of it, I don't care. But don't get confused over it. Remember, this was a confidence interval for mu3 minus mu1. It's entirely negative. And if it's entirely negative, that means the second number was the greater number. All right, so however you want to say that. And so what we're saying here is that on average, all third graders take anywhere from 3.97 to 18.03 minutes less to complete the math problem than all first graders. Okay, or you can switch it around and put first graders first, okay, and then the third graders second, and say that first graders take more time to complete, however you want to say that, okay, but just be careful on how you say it. Make sure that, I mean, I'll follow along on however you say it, all right, but make sure that it's proper, all right? All right, now that takes us to the end of the presentation. Thank you for your time today.